Alright, my name is Jeremy Leavell. I'm from the University of St. Thomas in St. Paul, Minnesota. This is my project about X-ray crystallography. And in our research group, we were interested in observing how organic compounds pack in the ways they do when they solidify into a solid state. And the molecules of interest to this study are one pair of isobaric phenylhydrosomes that we kind of term the bridge-flipped isomers. As you can see, we've synthesized these two products, and they're exactly the same, except they differ in their orientation about this phenylhydrosome bridge, which is a C double bond, so an N and then another N bridge. We were kind of wondering that if we get the crystal structure of one and study what sort of intermolecular forces determine how they pack, and if its isomer is the same but differs only about that bridge, we think maybe that might be close enough. Maybe there will be isostructure, so they have the same molecular packing arrangement, and this might lend themselves to being co-crystallizing, which co-crystallizing differing ratios of the two isomers into the same solid crystal may allow for the creation of new solid materials. The first isomer of our pair is this top one. We named it 4-chlorophenylhydrosome 4' metro. And we obtained that product first, ran the crystal structure of it using an X-ray diffractometer. And this is an ORTEP, Oak Ridge thermal ellipsoid plot of that compound with all the relevant unit cell data. And what we found in the crystal structure, as seen here, is that an oxygen atom from one of the nitro groups is in contact with both the CH and the NH hydrogens of the phenylhydrosome bridge of adjacent molecule. And also, there's extreme nitrogen-oxygen interactions between adjacent nitro groups. So, because of the interaction seen here, the oxygen is essentially treating both hydrogens as equivalent, and we surmise that in its isomer, where those two hydrogens are flipped, the crystal structure should be similar, if not the same. So what we did was we obtained the crystal structure of the second one, and just from a visual representation, they look very similar, which may have lent themselves to be isostructural. But when we actually determined the crystal structure, we found that there were many striking differences between the two. To begin, in the ORTEP of this one, we can see that there are two molecules in the asymmetric unit. That is, two molecules that are repeated to yield the unit cell, which the unit cell is then what's repeated in all directions to yield the overall crystal structure. Whereas its isomer only had one molecule in the asymmetric unit. And when we looked at the visual three-dimensional representation, we noticed that in this case, both oxygen atoms are in contact with one each of the two hydrogens on the bridge. Additionally, one of the oxygen also is in contact with the hydrogen on the adjacent benzene ring. This was very surprising. We're still kind of trying to figure out why that is. Another striking difference is that in this structure, the two nitro groups do not show the same contacts as they did in the previous structure. So once again, this was a very surprising find to us. Our current research is looking into why, if the oxygen seemingly prefers both hydrogens, why would suddenly in the isomer, which differs once again only in the orientation of that molecular bridge, why would that be different? So yeah, and if we can figure this out, we'd like to try a co-crystallization experiment. At this time, we feel that the differences between the two structures are really slight, and so it might be a good candidate for a seeding experiment, in which a crystal from one of the isomers is placed in a solution of the other, and that might serve as a template from which that isomeric compound might crystallize in the same manner as its partner. Therefore, they would form the same crystalline pattern, and thus might be ready for co-crystallization attempts. And that is currently the subject of our future work in this project.